Okay, so page 41, was that right?
Yeah.
Oh, this is a good question. So this is from your HSC Chemistry additional question booklet, right? Not the one that I made for you. This is the NESA one, right? So if you all just search right now, if you haven't seen this question before, NESA, HSC Chemistry, sample questions, there's an 80-page booklet with introduction questions for every single module of HSC Chem. And that's what I would recommend you start on for exam questions before jumping straight into trial questions. Okay, can you all see the screen?
No.
I must have tried the wrong link. Give me one moment. Okay, good. You should see it. You should all see it now. Okay, good. Who's done this question? Can you hit the raise hand icon if you've got an answer to it already? Good. Nathania has. Sid, take it away. So take us through your reasoning for this question, right? It's showing you particle gray reacting particle white to form this molecule. Sid, what's a simplified letter equation you could write for this?
I can just write black with circle equals both.
Yeah, so I'll just do A plus B. It's a synthesis reaction, right? So try writing it in chemical reaction format so you truly understand what's happening. So you see the initial reactants. And what's initially present in this vessel? Is it A, B, all three?
It has A and B.
Good. And maybe just quantify the number of molecules, because that might help you as well. We don't know because we haven't gone through the entire question, but there's 1, 2, 3, 4, 5, 6 molecules of A, and there's 1, 2, 3, 4 molecules of B. Okay, good. All right. So which combination of diagrams best represents dynamic and static equilibrium? So let's just quickly define those two words together. When there is equilibrium, what is the definition, Akshita?
So equilibrium is when the forward and backward reactions are occurring at the same rate, and when the concentration of all the reagents are stable.
Very good. Very good. Last lesson as well. Forward equals reverse reaction. Concentrations are constant. Very good. Okay, so what's the difference then between a dynamic and static equilibrium, Zainal?
Isn't dynamic where it's constantly reacting between products and reactants, and static just reacts and then can't react without an input of energy?
Good. So what can you tell me about the forward and reverse reaction rate in a dynamic equilibrium? 0?
Constant or equal?
Equal and greater than 0, because that's what you're telling me when you're saying there's a forward and reverse reaction. In the case of static equilibrium, it's 0. And the reason it's greater than 0 is because it's a reversible reaction and it's achieved that state of equilibrium, right? Good. And then this is an irreversible reaction. So very quickly just jotting those things down. Let's have a look at A. You need to work through the process of elimination in chemistry. Interestingly, the chem exam for students is happening on Monday. So all of my graduating batch now is sending me a lot of questions to fine-tune their understanding. So you guys will be sitting your exam in about 367 days. Anyway, coming back to this option A. Sid, what do you think about A? It's good, but it's bad.
I think A is good because with with the static diagram, you can see that the black circle there's like two lone ones, and there's no white ones on its own, which means that the white one was like the limiting reagent, so it's gone through completion. And with the dynamic one, you see there's both the reactants and products, which means that the reaction is still undergoing and it's reached some sort of equilibrium.
I like that answer. Very good, right? This is where the numbers really helps you, right? So you see there's 6A and 4B, okay? And if you just represented what's going on in the static equilibrium one, so this one here, you can see there's still 2A and there's been 4AB, which tells you there's been 4 rounds of this reaction here. Does everyone agree? So 4A got used up out of 6A, so there's 2A left. Tick, right? 4B got used up, there's no more B. And there's been 4 molecules of AB formed. Perfect. This is a really good example of static equilibrium. It's an irreversible reaction which has gone to completion, and the reason you're still seeing some of A is because that's the excess reagent. It has nothing else to react with. There's no B for it to react with. So as Sid mentioned, it's a perfect example. Dynamic equilibrium, again, I agree with him, right? There are some product molecules formed, and there are still some reactant molecules that can combine to form product. Right? So if it were a dynamic equilibrium, this would still be going. There'd be a forward and reverse reaction. So I like A. Let's go to B. What's good or bad about B? Let's go to Zainal. What do you think about B?
So the dynamic equilibrium doesn't seem to be balanced with static, so.
Let's look at it more specifically, because balance is a vague term, right? Is there a reverse reaction? Sorry, is there a forward reaction that can occur, Zainal, in B, in the dynamic equilibrium? No, right? There's no more A. Sorry, there's A. There's 2 molecules of A. There's 2A, but there's no B to react with it. If there's no B, you don't have a forward reaction. You don't have the reactants to form the products. So in this case, B, the forward reaction is equal to 0. You can't have a dynamic equilibrium. Straight away cross it out. Don't even look at the second diagram. Okay? Again, let's go to C. And what do you think about C?
Well, for C, there's no products at all for dynamic.
So can there be a reverse reaction?
No.
Good. So again, and it's identified, C is also wrong. Because in dynamic, what did we say? It has to be greater than 0. Finally, D. Let's go to Akshita. What do you think about D, Akshita?
So in static, there's like no products formed, so it doesn't show completion.
Very good. So now you looked at the other one that's also wrong, and this is also wrong, because then there's no white to react with the gray. There's no forward reaction. So all of them are wrong except A. So as Sid mentioned, A is the best answer. So very good, right? So that's how they're going to test you about static versus dynamic. Static is very low yield. This is like the hardest question we'll get, testing you on static equilibrium. Okay, good. Any other questions you'd like me to go through before I jump into the content, everyone? Okay, good. Let's move on. Let's go all the way down to these diagrams, do some more questions. So we would have left off at, done these questions, we've done this. Okay. What I'm about to teach you is very high yield, because it's going to be one layer deeper into your understanding of the Chatelier's principle. Sid, question?
I just wanted to clarify something.
Yep.
You know, in the cobalt chloride equilibrium, when the water, like, when it's blue, right, and there's water on the side, what state is it in?
Liquid.
Oh, okay.
The
Like,
water, yeah, question.
because when you heat it, right, and it becomes water vapor, like, I was a bit confused what state it would be in.
Okay, so your question was when you heat up that beaker, the water could be gaseous, is that right?
Yeah.
But that's an additional stress you're applying on the system. The equilibrium itself will produce water at a liquid state, and then whatever you do to the vessel can change the state of any of the substances, right? So we don't really account for that, if that makes sense. So we're talking about the states of an equilibrium, we're solely looking at if we did not disturb the equilibrium, what states would everything come out as? Then after that, whatever happens to the state doesn't matter. We just keep it as the initial state. Okay? Good. Good. All right, so let's go down very quickly. Who wants to define the Chatelier's principle? Let's go to Britannia. Can you define it for me? Exam answer.
Principle states when a reaction
at equilibrium is disturbed, the reaction will shift to partially counteract the disturbance.
Pretty good. I'm happy with that. Last thing I just added return to equilibrium, but perfect, right? Shows me that you've been teaching yourself, going through the homework, so very good. Sid, what are the 3 things that affect equilibrium?
Temperature, concentration, volume/pressure.
Good. And in what example, so what state equilibrium would volume/pressure affect the equilibrium?
Gaseous.
Okay, very good. So only in gaseous systems. Very good. And moving on to you, what are the 3 questions we always ask ourselves when we're answering LCP questions?
The stimulus,
Yep.
the opposite and direction.
Very good, right? And actually the final question, if I have an aqueous equilibrium system, and if I add water, have I disturbed the equilibrium or not? So everything's aqueous, I've added water. Will that disturb the equilibrium or not?
No.
Okay. Remember, whenever we go through hard, challenging questions that you don't get right, this is the most important part about science in general, right? I want you guys, ideally what you should do is you should have a separate book with all your mistakes. And every time you make a huge mistake or a big mistake in red, you should write down the mistake you made. And what you'll build over the year is every mistake you've made. And if you don't make those mistakes again in your exam, you'll get 100%. So that's simple if you've done enough questions, right? So last lesson, we did a question where no one knew the answer to that aqueous equilibrium question when we added water. Does anyone remember how water affects an aqueous equilibrium system?
Isn't it because add water, it affects the concentration of everything else?
Good. Very good. This is a very important principle you'll understand because especially in your trial exams, this is the questions they'll ask you because they know a lot of students don't remember or don't understand this concept, right? When you increase water, water is a liquid. You're not going to change the concentration of water. What you are doing is you're changing the concentration, decreasing it, of all other aqueous species. Okay, so if I was to ask you guys right now, the equilibrium in front of you right here, the iron thiocyanate equilibrium, if I added water, what color would the equilibrium become? Yellow or blood red? When you've got your answer, hit the raise hand icon. Good, so let's go to an answer. Apply those 3 questions, guys. And remember, the stimulus is the most important thing. You have to really nail down what has been affected. C, P/V, or T, temperature. Actually, you're going to take us through this now. So, what are the 3 questions you ask yourself, and what is the answer to those 3 questions?
So the question that I would ask myself would be, what was the stimulus? That would be the change in concentration.
Remember, change is too vague. What happens specifically to concentration and of what substance?
So the concentration of the iron and potassium would go lower.
Yeah, remember, there's no potassium here. I think you mean the thiocyanate, right? The
Thiocyanate,
Yeah, I'd say the concentration of all aqueous species have gone down. So I'd say decrease in concentration of all aqueous species. So what's the opposite of that?
An increase in concentration.
Good. So which direction would you want to go? There's 1 aqueous species on the right-hand side, and there's 2 on the left-hand side. Which direction are you going to make more aqueous species?
The left.
So we become yellow, right? Because iron 3 has a yellow color. Very good. That's it, right? So these questions become very easy. I want you guys to work on speed now, right? Work on speed in your exam answers. Most of you, Band 4 students onwards, will be able to answer general LCP questions. The point now I want you to differentiate yourself from your peers is by doing exam questions, so writing up exam answers. And second thing, being really fast, to the point where you can start doing it in your head. what is the stimulus, what is the opposite, what is the direction, I'm done. Okay, that'll help you a lot for module 5. Speed and then articulation. Good, let's move on. All right, you guys did very well for your quick review at the beginning of the lesson. Now, this dot point, 2.2, they love testing you on it. I've seen 2 years of HSC Chem papers where they ask about this dot point. Okay, so just read out the dot point and try to understand what's going on here, right? So I'm going to give you all 10 seconds to look at the dot point. Tell me, what do you need to know for this dot point? Especially those you've already learned it at school. Okay, SIP 2.2, like what are they really asking in a very dumbed down answer?
They're asking how the particles are affected with the changes to the equilibrium through collision theory. So how each change affects the amount of successful collisions and orientation.
Good. I like how you referenced particle collision theory. That was a very good answer. Now, one thing you would have all learned, when you ask the why question, you realize LCP doesn't really make that much sense, right? What did I tell you? I told you systems like to partially counteract change. The second you ask why, you reach a loophole. There's no why, just Le Chatelier's principle is a prediction system. It predicts the direction a reaction will go, but it doesn't explain why a reaction goes that way. Did you all realize that? Right? You apply the whole stimulus opposite direction, you'll get, okay, the reaction goes left because it wants to counteract the increase in sodium. Well, my question to you now is, why does this system, which has no belief sentience, want to counteract changes that we're imposing on it? Right? And the answer to that is Le Chatelier's principle is not explaining anything. It is a prediction system. The actual explanation for why a reaction goes a particular direction is based on particle collision theory. So in summary, what this means is LCP only predicts, does not explain, and LCP is a result of particle collision theory. And so to truly explain why a reaction goes a direction or left or right, you need to use particle collision theory. And then LCP will correlate with that. LCP, when you apply LCP, you go, yes, the reaction will go right as particle collision theory explained. Does that make sense to us? The link between particle collision theory and LCP. LCP predicts, does not explain anything. We have to use particle collision theory to truly explain why a reaction is moving in a direction. Any questions? Good. So I think Sid's already explained to us what particle collision theory is, right? So successful collisions only occur when reactant bonds are broken. And the 2 criteria for that is we need an energy greater than activation energy. And the second thing you mentioned, which a lot of students do miss, is particles need the correct orientation. Okay, so now what we're going to try doing, everyone, is I'm going to give you a stimulus for a reaction system, and we're going to explain it according to particle collision theory, and then link that to the equilibrium and direction it will go. Okay, so let's start by doing question. Let's do question 1. We'll start with a very simple question. Question 1. Let's say we're looking at this reaction here. Let's say we're doing. What's the name of this reaction? This one that I'm writing up for us. It's a very famous reaction. Anyone?
It's ammonia.
Yeah, do we know what the name of this reaction is? It's named after a German war scientist who tried to kill people. He would have tried to kill all of us if he'd seen us in today's age, right? Because we don't fit the Aryan phenotype. What is the name of this process?
The Haber process.
Yeah, Fritz Haber, German chemical scientist, tried to create ammonia so you can use it in gas chambers. Unfortunately, we found a way to use ammonia for good by reacting ammonia with hydrochloric acid or sulfuric acid to make ammonium salts. And ammonium salts contain the nitrogen that plants need to grow and develop. So we use that in fertilizer. We grew wheat, and now we can support a 7-point-something billion global population. Interestingly, as you guys go through life, I want you to be tracking the global population. Just every yearly or 6 months. By 2030, I think the population should exponentially increase to about 9 or 10 billion. Right now, we're already at 7 billion. And you can see on Sydney roads how packed everything is, right? So it's quite crazy to think the world is continually going to exponentially increase. A lot of implications for that, but we'll talk about that later. Good. Exothermic or endothermic? This one. It's exothermic, right? So we're going to write heat here as I encourage you to do so. So now, let's apply LCP first, right? Let's say I decrease ammonia. Which direction, Sid, will the reaction go?
It will reverse.
If I decrease ammonia, will it go to the reverse reaction or the forward?
Decrease. Okay. Yeah, it'll go to forward. It will shift to the right.
Okay, good. And Rithania, why is that? Can you explain it according to the Shadley's principle? So what's your exam answer for that?
By decreasing the concentration of ammonia, the system is interrupted. So you want to produce more ammonia according to the Shadley's principle. To partially counteract the change, we need to go to the right-hand side.
I'm happy with that answer, right? So you don't need to have the exact answer or template that I gave you, but that's good enough, right? It has the partially counteraction, it has a stimulus, and it has the opposite direction. Very good. But the second I ask you, why is that happening, right? Why are we partially counteracting? We have no clue. So that's what we're going to explain now. Now I want you all to approach it from a particle collision theory standpoint. When we talk about particle collision theory, I want you to break the reactants and products and think about them separately. Okay? So we're talking about collisions here, right? When I decrease the concentration of ammonia, am I affecting the number of forward particle collisions immediately? Yes or no? Am I affecting it or not? The forward collisions, so the collisions between the reactant particles.
No.
No, right? Because we're not changing the number of nitrogen or hydrogen, so they're going to keep going at a particular rate. But what's going to happen to the number of product collisions? Collisions between ammonia molecules that should reform nitrogen and hydrogen. Anyone tell me? If I decrease the concentration of ammonia, what is then going to happen to the number of products? So there's a decreased number of product molecules. So what does that mean for the number of product collisions or the frequency of product collisions? Up or down?
The collision will decrease.
Yes. There'll be a decrease in the frequency or the number of product collisions, right? Because there's less particles, there's going to be less collisions, less product collisions, right? Now, let's say at a particular temperature, 50% of collisions are successful. If I now have less collisions, what is that going to do to the number of successful collisions, where the product bonds are broken to form reactants? Everyone?
Decreased.
Exactly. So then you have to say there's thus going to be less successful collisions, and you should always define what a successful collision is in your exam answers. There'll be less successful collisions where product bonds are broken. Bonds broken. So guys, now I want you to tell me, we've thus said there's going to be a decreased reverse reaction. There is a fixed forward reaction that hasn't changed. When you have a decreased reverse reaction and relatively an increased forward reaction, which direction is the equilibrium going? To the left or to the right? Anyone? So we've literally just said, therefore the forward reaction is greater than the reverse reaction.
Go forward.
Yes. Therefore, the equilibrium is shifted to the right-hand side. So when the forward reaction is greater than the reverse reaction, for that small period of time, we're making more ammonia than we are making nitrogen and hydrogen. Remember what we said, concentrations at equilibrium are fixed. Everyone with me? So let's say, just to keep things simple, there's 10 molecules of nitrogen and hydrogen, and there's 10 molecules of ammonia, initially at equilibrium. When we disrupt the equilibrium through this by decreasing ammonia concentration, and when the forward reaction is being favored more than the reverse, what will happen is a number of molecules of nitrogen and hydrogen will decrease to less than 10, and the number of molecules of ammonia will increase to greater than 10. So I'm just going to pick random numbers off the top of my head. Let's say it goes to 6, and let's say this goes to 13. And then after that period of time, the forward and reverse reaction rates will become equal again. A new equilibrium would have formed. What has happened to the equilibrium position, everyone? We're initially at 10 and 10. What are we at now? The concentration is now 6 and 13. So what can you tell me about the equilibrium position? Has it shifted to the right? Has it shifted to the left?
Shifted to the right.
Exactly, and that's exactly what you mean when you say the forward reaction is being favored or the equilibrium will shift to the right, etc. So now, pause, forget this stuff. Let's talk about it in terms of LCP, right? Sid's already mentioned it, right? The stimulus opposite direction. When we decrease ammonia, we want to increase ammonia, we'll shift to the right-hand side. Do you see how LCP is a very shorthand way to predict what will happen according to particle collision theory? Right? That's all LCP is. It's just a little shortcut instead of going through all of these explanations to explain what will happen to the equilibrium. Good. So this whole dot point wants you to understand that the Chadley's principle is a prediction system and it is based on particle collision theory. And from now on, if they ever ask you to explain what will happen to an equilibrium according to particle collision theory, you're going to be talking about the number of collisions, the number of successful collisions, and comparing the two to tell me whether the equilibrium go to the right or go to the left. You will not be using LCP. Good. Now, I know we've just scraped the basics. So again, I'm going to give you another question. Question 2. And for this one, I'm not going to help you. I'm solely going to let you answer the question on your own to see how you go. And then we'll touch upon. So for the same equation, let's talk about the Haber process again, right? I want you all to explain why the reverse reaction would be favored when the reactant concentration is decreased using particle collision theory. I want an exam answer, like the one we have up. So when you've got your exam answer, hit the raise hand icon, and I'll ask one of you at random to explain that to me, okay? Good, we'll create some water. Okay, good. Sid's got an answer. Wait for one or two other people. Good. Fanny's got an answer. Good. All right. Let's go through question 2. So, Zainul, I'll get you to give it a go. So, give us an exam answer to this question.
So when the reactant concentration decreases, Le Chatelier's principle predicts that the particle collisions in the reactants decrease. So to partially counteract that imposed change, or
Pause for a moment. The second you mention partially counteract the imposed change, you're talking about LCP. You're not explaining it through particle collision theory. Did you see how here? Let me just read out my explanation to that question, the above question, right? When the concentration of ammonia is decreased, there's a decreased concentration of product molecules, and thus a decrease in the total number and frequency of product collisions, right? You'll say, as a result, the number of successful product collisions decreases where product bonds are broken. As a result, the reverse reaction rate is lower than the forward reaction rate. We can say the equilibrium has shifted to the right-hand side. Do you see how I never said anything about partially counteracting? Right?
That's how we should do it in the exam.
Exactly how you should do it in the exam. The second you talk about partially counteracting, you're talking about LCP. You're not talking about particle collision theory, right? So you're doing well. There's a decrease in concentration of reactants. There's a decrease in the number of reactant collisions. And then what?
Decrease in the successful collisions and the frequency.
Frequency. Technically, yep. What does that do for the forward reaction rate versus the reverse reaction rate? Remember, the reverse reaction rate is unchanged. That's on the right-hand side. What's happened to the forward reaction rate, Zainul?
Wouldn't it decrease because there's a decrease in concentration of the reactant?
Now, the forward reaction rate is less. The reverse reaction rate is greater. Which direction is the equilibrium going to go?
Wouldn't it shift to the left?
Exactly. If the reverse reaction rate is greater, the products are being shifted into the reactants. It's going to the left, right? Therefore, you will say, therefore, the equilibrium is thus shifted to the left. And that's your explanation. That's it. Anyone have any questions? Akshita, Britannia, Anne, any questions at all?
Could you explain the forward and reverse reaction bit of the question again?
Sure. Okay. So when we talk about forward and reverse reaction, right, Akshita, what we're talking about for the forward reaction, what I'm talking about is a number of reactant molecules, nitrogen, hydrogen, that will collide successfully to form ammonia. When I say reverse reaction rate, I'm talking about the number of molecules of what? Nitrogen, hydrogen, or ammonia?
Ammonia.
Ammonia, that will then collide with other ammonia molecules to reform nitrogen and hydrogen. Okay, good. So when we decrease the concentration of reactants, what's going to happen to the number of nitrogen and hydrogen molecules?
They'll stay the same.
If I decrease the concentration of reactants, the reactants are nitrogen and hydrogen, right? What's going to happen to the number of molecules? It's going to go down. Do you agree? Well, what is C? C is N on V. If I decrease the concentration of reactants, which are nitrogen and hydrogen, I decrease the number of molecules of nitrogen and hydrogen. Does that make sense?
Yeah.
Yeah. So as a result, there'll be less nitrogen and hydrogen colliding. And so what does that mean for the forward reaction? If there's less nitrogen and hydrogen successfully colliding to form ammonia, Remember, forward reaction is nitrogen and hydrogen colliding. So if there's less of them colliding, what does that do to the forward reaction?
Like a decrease in forward reaction, like it won't happen.
Yes, it'll decrease. It'll go down. It'll go down, right? And the reverse reaction is untouched. It'll stay the same because we haven't actually changed ammonia immediately, right? When we decrease the reactant concentration. So now, since the forward reaction rate is occurring lower than the reverse reaction rate, focus on what's occurring more. Don't compare the two, just focus on what's occurring more. The reverse reaction rate is occurring more. That's the key thing, right? So the net change is going to be that ammonia molecules will react and reform nitrogen and hydrogen. That's the net change that is occurring. We're increasing the concentration of reactants when we do that. So that's why we say the equilibrium shifts to the left. Okay? Since the reverse reaction is being favored more. Does that make sense?
Yeah, that makes more sense.
Good, good. Siddharth, question?
So while the reverse reaction rate is decreasing in the first question, does the forward reaction say the same?
Yes, it does stay the same immediately. But do you agree? It will change slowly, right? They equilibrate, right? What I mean by that is since the reverse reaction rate decreases, let's have a look at the forward reaction rate and the reverse reaction rate. Since the reverse reaction rate decreases, we're going to form less moles of nitrogen and hydrogen, right, Sid?
Yeah.
So eventually the forward reaction will come down a little bit as well. And they'll meet each other. But what I'm saying is initially the forward reaction rate will be unchanged when I change that stimulus.
Yeah.
Okay. You guys will understand this much more when we look at graphs of concentration on time. It'll make a lot more sense, okay? Just bear with me. Good. Now we're going to do some slightly harder questions. How would a change in temperature affect things according to particle collision theory? Now for this, very quickly, you need to understand energy profile diagrams. So this is A, this is B, this is C. So you know what's the activation? Oh, this kind of gives it away, the diagram. What's the enthalpy change for the reaction? Is it A, B, or C?
Isn't it B?
Actually, what's the enthalpy change for this reaction? A, B, or C?
A?
Good. It is A, right? When I say enthalpy change, all you need to do is where are the reactants, where are the products, what is that energy difference? That A value is the enthalpy change. All this B is activation energy, right? We don't care about that when talking about enthalpy change. Okay, enthalpy change is just what is the difference in energy between the reactant molecules and the product molecules. Okay, very good. Just appreciate what an energy diagram looks like, because that's going to help you understand how temperature affects reaction rate. Now, very briefly, what would happen? So according to particle collision theory, when I increase the temperature of a reaction, forget about LCP, forget about all this, use your year 11 understanding for this. When I increase temperature, how am I affecting reaction rate? Anyone?
There'll be more reactions happening because they have more energy, so they'll collide more.
Good. What I'd like you to all say first, though, is when I increase temperature, I increase the average kinetic energy of all molecules, right? So increase the kinetic energy of all particles. Okay? This will increase, it'll increase the number of collisions, but what does it also increase? Particles are not doing this anymore. They're doing
collisions by energy.
You're increasing the energy of collisions. It's the average energy of collisions. So what is that going to do to the percentage of collisions which are successful?
Increase.
Increase. Do you guys agree that does not happen when you increase concentration? When you increase concentration, you're just increasing the number of collisions. So we go from, let's say, 100 collisions per minute to 200 collisions per minute. And if 50% of them are successful, then the number of successful collisions goes from 50 per minute to 100 per minute. But did you see we did not change the percentage of collisions that are successful? It stays at 50%. The one thing that affects the percentage of total collisions that are successful is energy or temperature, which is going to increase the kinetic energy of the particles, right? So only for temperature do we say this specific point, that the percentage of successful collisions will increase. Now let's have a look at this graph so we truly understand what is happening, right? So this is an example of let me show you this. Yeah, don't worry about the endothermic, exothermic, it still will make a lot more sense. Here you have activation energy. Here you have number of molecules in the y-axis, and here you have the energy of all molecules, right? So what you can see in this first graph, graph number 1, forget about these two names and stuff. In graph number 1, what I see is most molecules have this amount of energy. The energy I need for the reaction to occur is here to the right. So most of those particles, will they engage in successful collisions or unsuccessful collisions, everyone?
Unsuccessful collision.
Very good. It's only that tiny number of particles here and onwards that have an energy greater than activation energy. So the area under the curve is very small, which is telling you a very small percentage of particles will actually successfully collide. The reaction rate is now low. But the second I increase temperature, I increase energy of all particles. So what you'll be able to appreciate is this graph. Forget out the graph on the right, I'm going to redraw it for you so you can truly appreciate it. The area under the curve must be the same always because the number of particles are fixed, but it will shift position to look like this. It'll become flatter, but it'll become wider. And now what you can appreciate is most particles now have an energy greater than the activation energy. And so now there's more successful collisions, greater percentage of successful collisions, the reaction rate has increased. Okay, so using this knowledge, I want you to now think, what will happen when I increase or decrease temperature according to particle collision theory? We'll use the same reaction, right? We'll use nitrogen plus hydrogen gives you ammonia. That's 2, 3, all gaseous, right? What will happen when I increase temperature? What will happen when I decrease temperature? It's a much harder question than the two we've done before this. So just think about that. And what I'll actually get you to do, because we've pretty much hit more than half time for today's lesson, since it's a bit shorter, take your 5-minute break now. We'll recap at about 4:57, and then I'll still give you a bit more time to digest this question. We'll go through it together. Okay? Good. Any questions before you take your break? All right, see you in 5 minutes. So stand up, stretch, get some water. Okay, when we're all back, let's hit the raise hand icon and I will move on. Good, good. All right, so I will posit the question to you again. So we'll start with question 1. I want you all to start hypothesizing or thinking. What I want you to do is, if they told you it's an exothermic reaction system, the first thing you want to do is draw the energy profile diagram. So what does the energy profile diagram look like, Anne, for an exothermic reaction?
The will be higher on the other side.
Yeah, so on the left-hand side, the reactant side will have a greater energy than the products because the system would have lost energy to the surroundings. So it'd look like this. Good. So that's the first thing you want to do. Now I want you guys to think about what would increasing temperature do for the forward reaction and what would it do for the reverse reaction? Think for about 20-30 seconds and then I will give you guys an analogy which really helps me understand this. Okay. Hit the raise hand icon once you've got a bit of an explanation or any idea. All right, so I understand it would be a bit confusing, so let's go through it together. I want you guys to imagine this is a mountain, right? This is a mountain. You can use many analogies. You can use a Mario Kart analogy. We'll just use a mountain analogy for now, right? I want you to imagine that you have a friend, and let's say your friend is up here, and you are down here. You both need to reach that mountain, okay? Your friend is, just to keep it very extreme in our analogy, let's say your friend is 10 meters away from that mountain, and you're 4 kilometers away from the mountain. Now, if I was to increase the temperature and give you an energy boost, or I could increase the temperature and give your friend an energy boost, who would benefit more from this energy boost? So you can treat it like a Mario Kart race, right? Your friend is 10 meters away from the finish line, you're 4 kilometers away. If you were to hit a mushroom which speeds you up, who would benefit more? The person who's 10 meters away or the person that's 4 kilometers away?
Person 4 kilometers away.
4 kilometers away, exactly, right? So this analogy is to help you kind of conceptualize that when we increase the temperature, sure, exactly like I said, we increase the kinetic energy of all particles. We increase the total number of collisions, but we also increase the percentage of successful collisions, right? Now, the only thing you need to add now for equilibrium reaction is, however, right? Since if we look at the activation energy for the reverse reaction is very high. The activation energy for the forward reaction is very small. So since the activation energy for the reverse reaction is much greater than the activation energy for the forward reaction, so again to say, since the activation energy for the reverse reaction is greater than the activation energy for the forward reaction, therefore the reverse reaction will increase its rate to a greater extent. And this is simply vocalizing or explaining that even though we're increasing the percentage of successful collisions, using our little diagram, our energy profile diagrams, right? If I was to graph the profile for the forward reaction, it will look like this. So remember, the activation energy is very low, and the graph will look like this. So most particles, most reactant particles for the forward reaction have an energy greater than activation energy. So if I was to increase the temperature even more, right, the graph would just downshift or shift to the right slightly. And there'll be a slightly greater increase in that forward reaction. Whereas for the reverse reaction, the activation energy is much higher, it's towards the right, and the graph looks like this. Only a tiny percentage, since their activation energy is so high, it's only a tiny percentage of product particles will collide successfully and form reactants. But when I increase temperature, since the activation energy is already so high, when the graph shifts to the right, can you see the huge difference it makes to the area under the curve? Right? So there'll be a much disproportionately greater increase in the reaction rate for the reverse reaction. Okay? And so now, to end it off, what we've said is increasing temperature will increase the kinetic energy of all particles. It'll increase the number and percentage of successful collisions where a reactant and product bonds are broken. But since the products have a significantly greater activation energy, they will benefit to a greater extent, and thus the reverse reaction rate will increase more. Which direction will the equilibrium shift? To the left or to the right? And left, right? So the reaction will shift to the left. Therefore, the equilibrium shifts to left. Now let's put this in LCP terms, right? Shifts left. Let's try explaining it according to LCP. Did we get it right according to LCP, right? Stimulus, opposite direction. Sid, take it away. So it's an exothermic reaction. We've increased temperature.
Since the temperature has increased, it wants to decrease temperature. And since it's an exothermic reaction, heat is on the left-hand side. So
if it's an exothermic reaction, is heat on the left or the right-hand side?
wouldn't it be on? It would be on the right. Yeah, it would be on the right-hand side. And then so it'd go the other way and shift to the left.
Yeah. It's the only thing is in your exam answer, you're not going to say heat is on the left, heat is on the right. That's for you to understand and write down, right? What you want to say is something along the lines of increasing temperature will cause the equilibrium to shift to the side which partially decreases temperature, right? Since the forward reaction is exothermic, the endothermic reverse reaction will be favored to partially decrease temperature and re-establish equilibrium position, something along those lines. So the opposite is decreasing temperature, so we want to favor the endothermic reaction, and so the direction we go is to the left because the forward reaction is exothermic. And good, did we get it right? We did. Now question time, ask away. Any and all questions. Sid, question?
So can you explain in collision theory why it favors the reverse reaction?
Yeah, for sure. It's because of this diagram that you see here, Sid, right? So again, I'll draw the diagram so we truly understand it, right? I'll start by just drawing the energy profile diagram, and then I'll introduce those diagrams. So the analogy is just to help you very quickly decipher and break it down. But according to collision theory, okay, so this is an exothermic reaction. Can everyone appreciate that? Okay. Now what I'm going to do underneath is I'm going to draw two graphs to show you the number of particles and the kinetic energy for the forward reaction, and also another graph for kinetic energy and number of particles for the reverse reaction. Everyone with me? Now Sid, what's the activation energy for the forward reaction? Is it high or is it low?
Much lower.
Yeah, it's much lower. So the activation energy for the forward reaction is here. The activation energy for the reverse reaction, all you have to do is go from the reactants or products to the activation energy. So activation energy for the reverse reaction is much, much greater. Does that make sense? So if I was to draw graph number 1, the activation energy would be, let's say here. And if I was to draw that curve of number of particles and their collective energies, so what you can see is, if I was to shade the area under the curve, already 97% of particles will engage in a successful collision, right? So if I increase the temperature further, and let's say we get this happening. We increase the temperature further. Now we've gone from 97% of particles having a successful collision to 99% of particles having a successful collision. Is that a significant increase in the forward reaction rate, Sid? It's very minimal, right? It's a very minimal increase in the forward reaction rate. But let's have a look at the reverse reaction rate. Okay, we're looking, according to particle collision theory, we're looking at the percentage of successful collisions here. So the explanation according to collision theory is, since the activation energy is so low, an increase in temperature results, or only results, in a small increase in the forward reaction rate. Okay, does that make sense so far? Yes?
Yeah, I kind of get where you're going with.
Yeah.
Yeah.
Whereas if we look at the, if we look at the reverse reaction rate, the activation energy is going to be all the way here. If we look at the graph now, right, initially, only about 1 or 2% of particles are engaging in a successful collision, the area under the curve, right? Should have done it like this. The area under the curve that's successful is only this small amount versus majority of the curve in a previous example, right? So we'll say the percentage of successful collisions is 2%. But when I increase temperature, and then the graph shifts to the right, the graph should be lower. So I'll make it a little bit lower, right? What you will now appreciate is the reaction rate has increased from about 2% to, let's say, 50%. Okay? So my answer according to particle collision theory would be, since the reverse reaction rate has a significantly greater activation energy, initially, there is a very low percentage of successful collisions. Therefore, increasing temperature will result in a greater percentage increase in successful collisions versus the forward reaction. Does that make sense?
So is it that like exothermic reactions have less activation energy than endothermic?
No. Exothermic reactions have a lower activation energy than their endothermic reverse reaction, yes. But you can't just as an absolute for different reactions. So when you're looking
at the same reactions.
For the same reaction, that's always going to be the case. For an exothermic reaction, the forward activation energy is always going to be very small. The reverse activation energy is always going to be very big. Yeah, that's just because of the shape of that graph. Good. Okay. Does that make sense to everyone? Do we need any clarification? Feel free to ask. This is a hard concept. This is probably one of the hardest concepts for Mod 5. Okay, I'll put you in the deep end and see how you go then. So question 2 and 3. When you guys get an answer to question 2 and question 3, hit the raise hand icon and we'll go through it. Try giving a quick, just give me dot point answers, please. Don't write a full 3-mark paragraph, just dot point, dot point, dot point, just as we've been doing in our questions here, okay? That's what you need to do and work on right now. Don't want verbose answers, I just want very concise, what are the key things I want to have in my answer. I'll get some of you to read it out as well, okay? Maybe 2 minutes. Good, some water. Okay. Can you hit the raise hand icon if you've got an answer to the first question? Good. Okay, I'll wait for a couple more people to get an answer. So, what career were you interested in for your future? That's good. Engineering. Nice. Okay. Why engineering? What interests you about it?
I want to go for electrical or mechatronic engineering because I have a passion for like robotics and electronics and stuff.
Very cool. Yeah. Engineering is a really good degree to help you create products, right? Infrastructure, technology as well. Electrical engineering particularly. I think it was either Elon Musk or another very famous founder of a company used electrical engineering to understand to start their business idea. Yeah. I think coding and electrical engineering go very well together. And when you combine those two and you're really good at what you do, especially in terms of a job security and income point of view, you'll be very well off. I think the rest of you were interested in medicine, is that right? Why medicine? I'll just very quickly ask Sid, what did you want to do medicine?
No, I'm more interested in the physics side, so a bit like Zainul, just engineering and more on the physics side.
Very cool. Mechatronic engineering, etc. Interestingly, a lot of doctors who are interested in physics go on to do radiology, where they do scans and such. It's, MRIs, for example, which are a lot of physics, and you have to do an advanced physics course after medical school for that as well. Pretty crazy.
You need a med degree for that?
Yeah, you do. So
Okay.
very long. And I would say what Sid's concern is very valid in the sense that I think the biggest con of medicine is you'll go through 6 years of studying and you'll see your friends leave 3-year degrees, start getting paid very early, get their house, get a car, start a family, and you'll still be a full-time student. So there will be a delay in your life transition to being a full adult. So that's something you all need to consider, and whether you're willing to sacrifice that. Good. All right, let's answer question 2. So, Rithanya, take it away.
Decreasing the temperature of an endothermic reaction will have less energy to reactant and products. And to increase the temperature, the forward reaction is less than the reverse reaction.
Pause for a moment. Do you realize how you said the stimulus is decreasing temperature, and then you went to increase temperature? The second you say that, you're talking about LCP, you're not talking about particle collision theory, right? Because particle collision theory is not about counteracting any change. That's LCP. Does that make sense, Rithanya? Right? So particle collision theory, all you want to talk about is successful collisions, and which side has more successful collisions, which side has less. Okay? Nothing about counteracting change. But very good. I like your beginning start off, right? Decreasing temperature will decrease the kinetic energy of all particles. I will get Akshita, keep going.
I said that the forward reaction would have less successful collisions than the reverse reaction because there's a higher activation energy.
Okay, very good. So now, like what we all should have done, and I'm sure Akshita did this, is you drew the energy profile diagram for an endothermic reaction. And then you have to compare the enthalpies, right? So the forward reaction enthalpy is humongous, or the activation energy, right? The reverse reaction activation energy is so tiny, right? So now, if we decrease temperature, who's going to get more hurt, right? Use our little analogy. Is it going to be the person that's 4 kilometers away? If you make them tired, is that going to be more of an impact versus making the person who's 10 meters from a hill tired? Who's going to be impacted more, everyone, when you decrease the kinetic energy of all particles?
Forward?
Yeah, the forward reaction. The person is 4 kilometers away. If you make them very tired and sleepy, they're not going to make to the top. Virtually no particles. So according to our analogy, if we convert that to scientific speaking terms, virtually no particles will have an energy greater than activation energy, right? Because activation energy is so high and we've decreased the temperature or energy even more, right? Whereas the reverse reaction, 98% of particles are successfully reacting because they're 10 meters from the endpoint, right? If you decrease the energy, sure, we go from 90% to 70%. But what I'm trying to say here is when we decrease the energy of all particles, it's going to affect the side which has a much greater activation energy more. So you say something along the lines of, as the forward reaction rate has a significantly greater activation energy than the reverse reaction rate, right? The percentage of successful collisions in the forward reaction will significantly decrease. What will that do to the forward versus reverse reactions? What we've currently said is the forward reaction will go significantly lower, and the reverse reaction rate will go lower, but by a little bit. So guys, what does that mean now for the position of equilibrium? Which direction will this equilibrium go?
Back.
What's our final answer? Let's try breaking down according to LCP and C. So if you're stuck, just break it down according to LCP. So let's say we have A plus B. It's an endothermic reaction. So Sid, which direction does heat go?
Heat is on the left. Sorry.
Right. So if I decrease temperature, right, what's the opposite of that? Anyone? Yeah, if we decrease temperature, the opposite of it is increasing temperature. How do we increase temperature? Which direction do we go, forward or reverse?
Forward.
If we go forward, we use up the heat. We decrease temperature, right? Because it's an endothermic reaction. So we'd actually have to go to the reverse direction. Okay, so in summary, for an endothermic reaction, if I decrease temperature, that's a stimulus opposite of increasing temperature, I want to shift to the left-hand side. So I need to reach this prediction of me having to shift to the left-hand side. So let's come back here, and let me just clarify what I mean by these percentages and reaction rates, right? So in our little example, since the activation energy is so high for the forward reaction, right? What's going to happen is the forward reaction rate initially would have been 2%, since activation energy is so high. When I decrease energy, it's going to now drop to 1%. That's a change in 1%. For our reverse reaction, initially, 90% of particles, let's say 99% of particles are successfully reacting. When I decrease the energy, it'll go from 99% to, let's say, 50%, right? 2% can't drop much lower than 2. 99% can drop a lot. That's a change of about 49%. So who's been affected more, the forward or reverse reaction rate? Just looking at the change in percentage. Pardon?
Yes. Reverse.
Yeah, the reverse reaction rate has been affected more. Very good. But having a look at the final changes, right? 1% now, we're at 50% now, right? So ultimately, we initially had a very low forward reaction rate. It's decreased now to 1%. We had a very high reverse reaction rate. It's decreased by a lot, but it's still significantly higher than the forward reaction rate. Does everyone agree? 50% is much greater than 1%. So which reaction is being favored? So our forward reaction rate is very small. Our reverse reaction rate is much bigger. So using our number analogy, it's 50%, which is much bigger than 1%. So which direction will the equilibrium go if the reverse reaction rate is proportionately still occurring at a much faster rate? Are you going to the left-hand side or the right-hand side? Sit. Left or right?
If the reverse reaction rate is higher,
Yep.
I'd go to the left.
Yeah. So let me just break things down in summary for you, right? So when you're trying to explain a temperature, this is probably the hardest question in terms of temperature collision theory. So I understand it can be confusing. So to break it down, always start with thinking about temperature and kinetic energy, right? So when we decrease temperature, we increase kinetic energy. When we decrease temperature, we decrease kinetic energy. The next thing I want you to compare is the activation energy for the forward reaction and the activation energy for the reverse reaction. Okay? If it's tough like a question like this, use examples, use numbers that can help you understand and compare the forward and reverse reaction rate, right? So that's what we did there. And the final thing you want to come to is, in the end, what will be the rate of forward reaction? What will be the rate of reverse reaction? So in our little thought experiment, the rate of forward reaction is only 1%, right? The rate of reverse reaction is 50%, much higher. And so we say the reverse reaction rate is occurring still much faster than the forward reaction rate, okay? And so the equilibrium will shift towards the left. Okay. Okay, I think the only thing I'll change, I think, to help you out with your answers, the percentage of successful collisions in forward reaction and reverse reaction rate will decrease, but the reverse reaction rate will be greater than the forward reaction rate, which is just this point here. Good. So in summary, an example answer would look something along the lines of this. So feel free to jot down anything that I'm about to say. Okay. Decreasing temperature in a reaction system will decrease the average kinetic energy of all particles. Okay. In an endothermic reaction, the forward reaction has a significantly higher activation energy than the reverse reaction. As a result, a very small proportion of reactant molecules will successfully collide to form products. Decreasing kinetic energy will further decrease the percentage of reactant molecules that can combine to form the product. As a result, the reverse reaction rate will be much greater than the forward reaction rate. The equilibrium will shift towards the left. That would be a little exam answer that I would write. Good. Any questions at all, guys? Okay. We'll continue off with this next lesson. Would you all prefer to do 30 minutes longer next lesson, or would you like to do 15 minutes longer for 2 lessons? Can you hit the raise hand icon if you prefer 15 minutes longer for 2 lessons? Okay, and hit the raise hand icon if you're happy with doing 30 minutes longer next week. Good. And can you make it? Okay, good. All right, perfect. So next week we'll be going from 4 to 6:30. Okay, and I'll give you maybe a 10-minute break in between. You're good. All right, good job. What I want you to do now is, there's a lot of questions we've skipped, and also at the same time, if you go straight down to the end of this theory book, go all the way to the end, there's a ton of questions for you to do. So what I would start doing is start skimming through. What I've done is I've collated all the questions by trial paper, but they're all Mod 5 related. So start looking at the questions and seeing the questions you can do. For example, you would be able to do question 2. You would be able to do question 1 of TEC. You should know which questions are relevant to you and not. So any of the K questions are not relevant, etc. But any questions you can do, do it. For example, all these questions. Perfect. Question 8. Right? So start doing those questions. If you have any questions, bring it up in class. I'll go through it with us. Okay? Good. All right, guys. Good job. Good revision and practice. If you have any questions at all, any assessments, bring it up with me. Otherwise, I will see you next week. Have a good week.
Thank you.
Thank you.
Bye.
Thank you.
Bye, Nathaniel. Bye, Sid. Bye, Zainul.